Thanks, Frank. So that brings us to the final point in our program, which is going to be the panel discussion. And Ben Upcroft is going to lead through the panel. If you can please get all the invited speakers to come up and have a seat here on the stage, please.
This mic. We had more invited speakers than this. Hey, Peter, do you want to come up here? Who else do we have? Oh, excellent. So now you can really heckle. The idea behind this is I guess the question of this whole workshop, are the skeptics right? I'm going to start off saying, it looks to me that deep learning can do everything. End to end, in the middle, doesn't matter. It was really inspiring today to see some of these talks and what you can do with deep learning and what maybe you can't. We had a whole bunch of questions submitted to our Deep Questions website. I'm going to start one, which I don't think was answered or really touched on during the whole set of talks, was online learning with a deep architecture. Is it possible? Do we care? Do we not care? I might start off with the panel. Now, can we do online learning in real time when it's deployed in the real world?
Yes.
Oh, okay. Next question.
I think that online learning, I mean, that's what DeepRL pretty much has to do, even if you add things like memory buffers to try to stabilize it, but it's still essentially online learning, and it is trickier, but I think that recent work has shown that it is quite, that it works and you can learn very powerful things because you're learning a sequence of You're learning from sequential data, and I don't know, it does work.
There is exploration. Oh, go do that, yeah.
Yeah, I totally agree on that. And I think, as I mentioned, also I think in robotics, one of the advantages is that we get this temporal data. So if, for example, you want to learn temporal models or things like that, dynamics models, then clearly kind of the future always gives you the training data, the label training data for the present, right? So I think continuously updating these models and keeping on learning is clearly feasible.
So this might be a dumb question, but exploration during RL can be bad, I guess, for a robot. It falls off the edge of a cliff, lands into something, drives into something, hits something, can damage it. Is there a limitation to that, or if we bootstrap it first, do we limit that space for exploration?
I mean, I think that safety is a really important problem, and anybody who has actual robots spends quite a while ensuring that they're not going to get broken immediately, and so those safeties have to be in place. And I think that going to probably Ashutosh has the most experience with deploying in the real world and making sure that things are safe.
I think exploration is obviously important, and I think one thing one can strategize about is assign a cost to exploration, right? Like simulation exploration is much more cheaper, so they'll make more mistakes, have a learned model, try to learn small modules from online data or from simulation. Once you get into the real world, try to explore in the direction in which the case the robot makes a mistake, it doesn't break down, and that's how you do things. It becomes even more drastic when humans are involved. So in my lab and many other projects, the robots are directly working in presence of humans. And then it becomes even more interesting on how do you even explore and when you can hurt the human.
I might open the questions to the floor if you haven't submitted something to the web page. Is there any would you like to answer a question? Ask a question?
I just wanted to follow up on the safety part. So how would you formally introduce safety into neural networks? Like formally guaranteeing if I have a flying vehicle that learns, that it's never crashing?
I mean, can you really do that for any other system? I mean, I know that people have proven software systems, but I mean, planes still crash. I think, you know, I mean, that's an illusion to prove a plane will not crash, right? Just put a bomb on it and then...
I think a more practical answer is that there are two ways to do it. One is to assign statistics to learning models. So you can at least say with certain probability under certain models, and yes, we all know that a 3 sigma event cannot happen and it still resulted in 2008 crash of the financial institutions, but at least we can start. The second one is to have hard bounds. Well, if you're a robot, I don't know about the flying drones example, but if you're working with robot manipulators, well, then put a hard bound that no more than this much force allowed and no more than this much amount of contact allowed, and that can at least guarantee some behavior.
I used to switch at the bottom.
I think we need to introduce concepts from failure prediction and lifetime analysis in other areas of engineering. These are fairly well-developed techniques and approaches that are used in things like manufacturing. And we rarely see that in machine learning, robotics, computer vision. It's probably time to reconsider some of those things as we have consumer-facing products.
And so I think in the UAV domain, I can well imagine that people already are developing, right, kind of almost proofs of stability and all these kind of things. And there clearly, these techniques have huge advantages over, let's say, just the kind of deep learning techniques. But if you go to, I guess, autonomous driving, or if you want to have a robot operating in the home and how you're going to prove that it's not going to let an object drop to the floor, then even the formal methods that people apply right now don't really work very well, right? Because you have to make many, many assumptions in order to prove things. But on the other hand, I think the deep learning community really has to go a long way still to improve on those things so that we can not maybe improve stability and things like that, but at least that we have a better understanding of what's going on. And just one final, and I think for many of those techniques, in the end, it's going to be like, can you drive a car for 100,000 miles without crashing it at all, right? So the proof will be maybe more in real-world experiments and showing that it's actually really stable there.
One thing that helps is that a lot of the deep networks have an array of outputs, and by looking at that, you can determine whether or not you can have confidence in the output. So if you have low confidence, then you would do something to prevent a crash. On the other hand, you're never going to be able to guarantee that you always have safety. So, for example, supposing that you're driving on a rainy day and you see a puddle in front of you, most likely the puddle is an inch deep, and if you drive over it, nothing bad's going to happen. But you can't, there's no way to tell that it's not 3 feet deep, right? So there's a situation where bad things can happen and you can't do anything about it.
New question. I think I've heard two camp. Oh, yeah, go for it. And yell.
So if you have one of these endpoint learning systems that's going a car or whatever road, if you encounter a situation where it's going to go bad, if you have a system based on rules or some set of handwritten knowledge, you can always look at logs and then try to go back and patch and modify the system to avoid that situation. What do you do if you just have neural networks? Go out and collect more data and just wish for things to go better next time? You cannot guarantee perhaps you have a rule-based system, but you can roughly certain that you can dispatch it to the situation.
So one of the things that you do is drive the car, have a human drive the car, and then also log what the car would do if it were driving by itself. And then you capture the events when what the network wants to do is different than what the driver wants to do. So you don't even wait to have a crash, right? You don't wait for bad things to happen. You look where there's a discrepancy between what the human driver would do and what the network wants to do. And when you collect those events, those are your gems. And those are what you train on. And you can in addition, you can do things like I described where we can shift vehicles around, do some rotations, whatever. You can take those events and you can expand events like that by modifying the scene. So you have somewhat larger distribution of those events. And you just train on that, and then you can test your network and see if it's learned that. And you also do a regression test to make certain that in doing that you haven't broken something else. So that's the procedure. It's not so different than what you would do with a rule-based system.
So I think there is a nuanced answer to when you use the phrase end-to-end learning. I haven't seen a single system used in real closed-loop system, a physical system where there is something sense, some learning, some control, and going out, and it's end-to-end learning. I think the real systems are somewhat modular, so you can put in hooks where you say, okay, I was trying to have this part of the neural network which was dealing with this sensing, is it misbehaving? Is it this thing misbehaving? Or is this a RL module which was misbehaving? So I think by having some interpretability in the machine learning models can affect things. And that's, I think, how the real systems are actually built when building these things like assistive or self-driving cars, or for that matter, in my lab, like robots and so on.
I think if I can ask you back something. Yes, you. So it seems like your question, there was the underlying assumption that somehow if you involve a human in incrementally fixing the system, that's a safer thing to do than if you involve an algorithm?
Not necessarily. As I said, the human programming system has a better understanding of why things are happening.
So yes, I would say you think the human has a better understanding than, say, backprop, right? If you just use a new data point, and I think that assumption is actually wrong. I personally would much rather fly in an automatic plane than in a plane with a pilot, because you look at the number of crashes, 95%. This is a made-up number. Are caused by human error, right?
One actually related, but by the way, you're on the wrong side here, right? You should be against. No, I'm just kidding. Another example might be when you looked at the DeepMind, the AlphaGo, right? Like, imagine AlphaGo does a move, and there were cases where people argued that it was actually not the right move, right? It does a wrong move. Clearly, how you're not going to easily look in the network and say, like, this is the weight where you did something wrong. But now, what's the alternative, right? Do we have rule-based systems that could even come to that complexity so that you could identify the tweak and make it work better, right? It's a very good question actually. So I just don't know how we're going to fix that.
So my car has a cruise control, like intelligent cruise control, so it stays. I don't know if that's how it
I really think if you try to answer it, you come to the point that our current policies for deploying systems are totally bogus and are just making us feel good because we have some legal stamp of approval that really they don't mean anything, right? And so I think it's going to make us more honest. Absolutely. So as you said, through learned lessons, right? So planes crash, they look what went wrong, and they fix it. And I think that's the only, they also say we have verified and proven and automatically deducted, Well, you know, I can make the swing now. I agree with you, but that is orthogonal to the question of whether it's a human or a system, right? We need priors, which you call understanding, right? And I think we need them in any kind of system.
No, actually, no. So when I say understanding, actually models. I don't mean priors, I mean models.
Well, a model, okay, now we are back in the discussion whether it's prior or knowledge or whatever, but to me a model is something you can help, that reflects structure in the world that you can put into your learning algorithm, or you should be able to put into your learning algorithm to make it more effective.
But I guess I would disagree with you in that I think priors and constraints are different, in the sense the example of the question this morning was data will eventually wash away the prior, whereas a model cannot get washed away. So, like, you know, in the airplane, so in the safety constraint, you know, you cannot, you're absolutely not allowed to have cracks in the fuselage, for instance. That's a really hard constraint. There's a lot of data about why the cracks will ever undo.
Okay, I mean, that's a philosophical discussion that we can have over beer. Well, so wouldn't you want your model? I mean, so you know, there's wear and tear in material, right? So now you can either put that into your model. It's you know,
No, you say that must never happen.
where do you draw the line? I mean, it's.
Here's an example. If I had a test, right, so Elon Musk is now deploying his autopilot, and I believe there's components of deep learning. So who's to say that, well, a particular combination of inputs will yank the steering wheel hard left right into upcoming traffic?
Isn't it?
So
Isn't that the same question as what Google's been doing? Like, even though they weren't doing deep learning, it's still the same problem, right? And they just did regression tests over a lot of data.
that's an interesting question. It's, you know,
I think the difference is here.
if you control, there's a certain level of understanding as to what goes in, and you can have actually some sort of guarantees to what inputs will lead to what outputs. If there is a network in there, you know, the question is, can we provide these same guarantees?
I think the question is twofold. Like, how do you learn these models and how do you test it? So you mentioned regression testing. In a physical products, you have deterministic tests, like where you can do some things. And most physical, like aeroplane systems, are what probably other people know better. They have deterministic tests, like this will not happen, for example, fuselage. Now, I think you were talking about a slightly different setting where the learning could still happen through a statistical model in priors, and you can still have deterministic tests. So I think this is a good area of research where how do you combine such learned behavior and tests.
The problem often is that the dimensionality of the input, say for perception, is enormous. Even though most images are not possible in the real world, but there's enough that you can't go through that and enumerate. And you can imagine that there's a suite of sensors on a car looking out in the road, and it's just ambiguous about what's there. And it's not possible to just reach in there by hand and say, well, what was wrong here is I've got to fix this little piece. It doesn't work that way. I mean, that's certainly true if it's a simple system with a small number of degrees of freedom. But when you have so much high dimensionality, it's not feasible to hand tweak, and it's not feasible to make absolute guarantees of any kind of behavior.
And I think that the same thing is true on an airplane as well, right? I mean, we cannot model. We think that the airplane is robust and that the engineering that goes into it and the safety systems are all robust based on empirical evidence and science, but that we're not going to be able to model every single weather system, for example, or all of the faults that could happen. So there's a certain amount of trust, and I think that that will emerge as well with self-driving cars. Especially given the fact that self-driving cars stand to save an enormous number of lives, Same thing with deep learning or machine learning in general moving into healthcare. There are a huge number of lives that stand to be saved, and there may well be accidents along the way. I think something is bound to eventually happen, but I think that the engineering and the science and experiments will... Yes, and that's modeled in the face of things like weather, bad weather. And it's not going to be exact in the same way that we can't test every image.
I think it's really incorrect to say that we really don't understand what's happening because of bad weather.
No, I'm saying that we do understand, and we also understand what the case is of the self-driving car in various incremental weather. But you can't enumerate all possibilities, all possible images in the same way that the model can't accurately simulate. You can't calculate the effect of all weather systems.
So, Nick, I wanted just to give you a few numbers.
This poor fellow here, he's got
Let me just get the numbers out. About 1 million people are killed every year by automobiles. That corresponds to about 10 747s crashing every day. So there's a lot of room for improvement here.
So that's true, but it's still incorrect to say that this is like that other thing. They're very different. Now, the gains to be had by giving up on rigorous modeling might be high in the case of traffic flows. I have no argument there. But the statement that I want to take issue with is that these kinds of learning techniques will be tested the same way that everything else is. They cannot be, they will not be.
I agree, and I see with the okay, yeah.
It's going to be an awesome question now.
I personally totally agree. And I think I hinted in my talk at these kind of notions of for tracking and things like that, how can you really combine model-based technique with the learning-based techniques, and it has to be a tight integration between those. And I think that's actually a lot of good research to be done, right? One question with respect to the airplane setting is, I think the question is whether we will be able to really translate those kind of techniques to the car driving setting, right? Because in airplanes, you don't worry that much about being able to detect people and trees and all these things, right? So the environment is, I dare to say, far simpler than on an autonomous car, because now suddenly, do we need to have guarantees on the ability to detect people and to predict their intentions on how they're moving, where they're going to move, and what they want to do, and things like that? I don't think we'll ever get the kind of models that we have for airplanes right now, right? Just because it's a much more complex setting that starts from raw visual image data at some point, right? So I think we need to come up with new ways of evaluating and proving properties of these systems.
That's blasphemy.
But I actually think we will get there. Just, it requires actually thinking about these issues. And maybe in some cases we have to give up the guarantees, because Larry's right. We'll save more lives by not putting ourselves in aviation security.
There's a comment up over there.
I would like to, I think there is an idea here which kind of resonates with what just Dieter said, what you said, and what you said. I don't think in physical systems like robots, you can have a 10,000 dimensional input and 100 dimensional output and a giant dimension in the middle like a big barrel. I think the real systems have to be modular and interpretable. So if you take these components, which take a high dimensional input, create a neck in that high dimensionality at different points along the pipeline, then each of those modules have a reduced output. You can actually enumerate the scenarios. So as much as we say that car is taking 10,000 or 100,000 pixels and creating an outcome, that is not true. If you take the car's output and create a well-defined input, which is the distances to car and some labels, that's a much smaller dimension. And you can actually evaluate the next step, which is control, in which you deterministically evaluate with all the outcomes what is going to happen. And that is what is reflecting to putting some manual intuition into the system or a structure into the models. So you can actually test these small pieces, and that's how one can, I think, go towards reliability.
That's a nice segue, Ashutosh. I think I've heard two camps today. Maybe it's just my imagination, but one says you can do end-to-end learning, and one says you need to split it up and be able to train them separately. It's slightly different to what you were saying before, where you could test different parts of it. But I'm wondering if you could comment on, I'm kind of with the end-to-end learning. I think you can do a big chunk of end-to-end learning with the analysis, intermediate analysis. But I wanted to hear what the panel says to that.
So to go with that, but also to respond to the question of what happens when one really bad thing happens and you have a big neural network, I think that reinforcement learning actually gives you a really good way of responding to that. So when we touch a hot stove when we're a child, maybe don't, hopefully we don't, but if we do, then we don't need to do that a lot of times to get the distribution right, touch a lot of different stoves in different circumstances. We just need to do it once, and the negative reward is enough. So I think that, and that naturally fits into reward-based learning, and I think that we should be able to solve this sort of thing in that way, possibly.
There's also a lower level control system going on here that's automatically, reflexively remove your hand independent of that higher level learning.
Well,
and that is an argument against that network. It's either independently learn reflexively or develop.
You still have to see the stove.
For future time,
yeah.
But I mean, before you even see the stove necessarily, you remove your hand just because of the nerve response. And so that's independent of this higher level concept of stoves or things that can be hot sometimes. And after I make a mess cooking, I have to wait some time to clean up the stove and touch it without hurting myself. So I think that simplifying the control process is happening in the human and ignoring these other components that aren't part of this higher level learning.
I also agree with both of you, also with Raia, that conceptually, of course, we should be able through reinforcement learning to learn these kind of things. But of course, also, I guess we agree that right now, where people are in deep learning, is we're clearly not there yet. That we have the network structure that can use this single kind of reward and then suddenly learn the right things, because learning that you shouldn't touch the stove requires also learning to detect future stoves and all these kind of things. So there's really some very, very complex reasoning that has to go on. And it seems many people think like deep learning is all this kind of, we just throw a huge network at our problem and then we try to solve it. But the research community is really looking into what are the structures of these networks, how can we learn different components, and it's going to be, I think, much closer to, let's say, graphical model kind of reasoning, right, where you have certain components that are good at certain things and how you can train new things without unlearning previous stuff. So there's still a lot of work to be done, but I think in 5-10 years, people will make the necessary progress.
I think one thing we've kind of been dancing around here too is generative models. In impoverished data regimes, this is really, really useful. You have one instance of some catastrophe. Sure, it's limited training data, but if I can build a generative model that might be able to hypothesize related instances, I now have more data to extrapolate from. And this in vision is a very, very popular idea. Again, it comes in waves, it seems, but we're thinking a lot about that these days.
I just want to jump in a little bit because of the skeptics in the title. So I think your question or your comment regarding withdrawing from the plate, from the stove, also alludes to some other thing, right? We're talking about robotics being a learning problem, right? I mean, that's sort of the only perspective that we have here, but I mean, I think robots are embodied physical systems, and somehow we've been completely ignoring that in our discussion. We saw the timeline of evolution, and you know, we're ignoring that our brain was built on top of millions of years of lower level neural function, right? So I think we're very myopically focused on this brain metaphor. You know, there's way more to robotics. There's way more to learning. There's way more to intelligence than what we're talking about here. And I guess that was a skeptical remark. I completely agree. I mean, it goes in both ways, right? It goes lower level in the sense that, as you described it, it also goes higher level. I think Pieter raised the question, you know, we basically have the same brain that we had. I mean, we basically have the same brain that apes have, right? I mean, there's no significant difference. And by the way, some birds have architecturally very different brains, but seem to be, as we're discovering bit by bit, seem to be capable of many of the same cognitive things that we are capable of. So I think, you know, we're in for a big surprise that, you know, we're not that special. So if you look at neuroscientists and if you look at anthropologists and they try to explain the difference between humans and apes, you cannot explain it with genetic differences. It's not our brain as a general that is a sole explanation for the difference. There seem to be social aspects. So you know, it's not only lower level, it's also going higher. That many of the things that we're trying to do with deep learning are a result of cultural learning. And so, you know, I think, like I said, I think we're myopic along very many dimensions. Well, I don't know about fire. It's true that we can obviously, you know, we were talking about 747s, building them and crashing them. That's something that animals. Yeah. So this is actually a very hotly researched topic, right? And I think the most current theories are saying that the size of our brain is predominantly there for memory. So actually, it seems to be that brain size and intelligence is not very correlated, whereas brain size and your ability to memorize random facts is very highly correlated. So it's true, you know, that through cooked food, we could develop a much bigger, much more energy, hungry brain. Thank you. But it's unclear whether this is something that actually replicates qualitative cognitive differences, or is just sort of memory, which then, in conjunction with the cultural learning, can actually play a role in actually, you know, then really being a difference, right? But I think the level that we're at, labeling pictures and so on, or recognizing objects in images, this is not necessarily affected by this.
I guess I would say the memory part of it, in fact, deep learning might be the best instance we have of memory being very
So I'd like.
Yeah, so language, there's sort of two schools, language and culture. I think ultimately, if you think it through, they end up being the same. But of course, these two camps are fighting, just like the deep learning people and the skeptics are fighting. They're also fighting.
So I will come down on the side of pure sort of end-to-end as opposed to a more modular response, because even though what I presented, one could say was modular, but let's ignore that. I just think that maybe to make this work, that we're always looking at it in too narrow of a way. So yes, there is an embodied body on our robot, as it is on us, and we need to have inputs to this deep neural network that are internal from the body, proprioception, et cetera, and our external senses. And those all have to be coming in. That's the only way that we can get a rich enough picture of the world that we're in. And the outputs, we need to not have just supervised learning and not just unsupervised learning and not just reinforcement learning, but all of those in order to be able to have a rich enough learning atmosphere in order to train it. And I think that if we have that sort of training and those sorts of rich inputs, then yes, we can learn a tremendous amount of very, very complex, intelligent behaviors for that robot.
I want to agree with Raia and also say that you can certainly have an end-to-end system, but it doesn't mean you can't have diagnostics that give you some hints about what the system sees. So you could imagine having an end-to-end system that goes from imagery to a steering angle, but you also could have diagnostic internally to discover that it's seeing lines in the road or it's seeing cars in front of it. But it doesn't mean you have to neck it down and have a five-dimensional vector that's supposed to represent everything that's important. You still can have that large space all the way through.
I just want to make one comment. You know, the views expressed here very much reflect dualism by Descartes, which is sort of the idea that there's a body and a mind. And in pretty much all disciplines except for ours, philosophy, cognitive science, and so on, this has been sort of past, right? This is not accepted anymore. There's the mind is the body, the body is the mind, and somehow I think we are ignoring that most of the structure that I think we need to do any kind of useful learning is when you consider the two together, right? So this separation of okay, we have what would you say? We have a robot on our, or we have a body on our brain or something you said. I think this distinction doesn't make sense because what comes to our brain has already been filtered significantly by the rest of our body. And so this is a unit, at least in us, that it's very difficult, if not impossible, to separate.
So actually I have a question. Do we still have any skeptics? Like, okay. Okay, great. So maybe we can hear some more. One thing is, I think it's easy to look at, here are some limitations, what deep learning cannot do yet. But it's also interesting to take maybe a meta perspective that's saying, okay, how many breakthroughs have happened in how many years? And so if you can enumerate only 5 things it cannot do yet, then maybe 5 years from now, that's all resolved. For example, let's think about the safety. One way to do safety would be to say, sure, if you've never seen something before, there's no way you can deal with that because you've never been exposed to this world. Let's say we go to a new galaxy and we try to do something there, we're probably not going to succeed first time around because the loss will be different. But let's say now you run an unsupervised learning algorithm that runs in parallel to your car that's trained to be driven, and it is really good. It's like the superstar variational autoencoder that is able to assign only probability to things that it sees and that are similar to what it sees, and then it sees something new. That autoencoder will say, this is essentially 0 probability under the model I've been trained, so we stand no chance in this situation. And it would actually trigger some kind of safety mechanism. It would say, oh, this is out of distribution, out of training distribution. And so I think at least that trigger, I could see that trigger existing within the next 2 years if variational autoencoders and related works continued the way they have been going, actually.
Can you define skeptic? I mean, what we're talking about believing, so now we're in religion. That's okay. But what do you have to believe to be part of your club, and what do you not have to believe to count as a skeptic? I mean, where is the dividing line here? What is the gospel?
I think it's maybe in my subjective mind, very subjective mind, it's the horizon over which you are thinking. So, do you want a system that can do something for you 5 years from now? Or do you want to work on something that is likely to be part of what will ultimately be the solution maybe 100 years from now? And I think the longer for you think, the more general your system needs to be, and the capabilities become very different that you expect from the system. Whereas if you want an airplane today, then you need to rely on the tools that exist today.
But hold on, isn't it our job to develop new tools? I mean, isn't that what we're being paid for? I mean, using existing tools to build stuff, isn't that called industry?
Sure, but there's different. There's different goals you could have. You could have the goal of having let's say, a self-driving car, and then you could cut some corners like Baidu is trying to do and say, hey, let's talk to the government and put some extra signaling on the street to tackle the problem of self-driving cars versus tackling the problem of general intelligence. And so I think that's a very similar kind of debate. Are you willing to put in this extra stuff, or do you see it as a challenge problem to get to something bigger in the long run?
Yeah, and I wouldn't put it as we roboticists are just using those tools that the deep learning community generates, right? We are, I think, in the position to identify the limitations of those and then work on maybe resolving them, right? Because we know in the context of robotics, certain tasks have to be solved, or we need a notion of uncertainty, we need to have a notion of, I've never seen that kind of data before. So I think it goes well beyond just being kind of people who are applying these networks. And also turning the point around with like skeptics or like the deep learning people. I'm also, of course, a skeptic, but at the same time, I think there's just a huge potential there, right? And the question is, I saw 4 hands up for skeptics. I think somewhat we are all still skeptic, but I think the ones who put up their hands, they are super skeptic or what? I don't know. It's, they just think it's all bogus, or who thinks it's totally bogus?
I got a question.
Look at this,
Matt.
Right?
Okay, so this is sort of a meta question, I guess. It's on the state of the field and where we see it going. So one of the reasons I did robotics, not vision, is I saw this trend towards people continually optimizing data sets. I think that's been a lot of benefit, but also you go to a conference now, and if I watch somebody give me a 30-minute talk about getting 1 to 2% more on a vision data set, I want to shoot myself. So how do we prevent robotics from descending into whatever that local minima is that the vision community is in, where I don't know if we're moving towards general intelligence with pure CV, and are we going to do that same thing in robotics and end up kind of optimizing? Maybe we solve self-driving cars, which is great, but if we solve it by just getting a really, really big network that learns enough things to be able to do that one task, where are we going as a field, I guess?
I think that's an excellent point. We actually had at ICRA, we had a workshop on data sets, right, where some people argued, okay, the vision community, they've done the right thing because they designed all these large-scale data sets, and now you have something that you can evaluate your different techniques on. In robotics, we don't really have that yet. So on the one hand side, I think you could argue we need some more data sets so that we can really compare our algorithms, but at the same time, there's a huge risk that everybody is just overfitting to those data sets. And I fully agree with you that we need to be very, very careful in how we design these data sets to be open-ended enough so that it's also doesn't guide the community into these kind of not dead end, but niches, right, where you're just focusing on getting another 1 or 2% to publish your paper. I totally agree on that.
I mean, I just wanted to respond to Pieter, and I guess also maybe to you. I think, we should use every tool that works. And why wouldn't we? I mean, that makes perfect sense. And if you have a tool that works and it does something useful, who would be against using that to do something useful? I mean, that's so then I'm in your camp. I mean.
So what are the problems we should use hyperparametric function parts?
So, but I mean, my point.
Is it really the tool for every single problem? I think Raia is probably
That's, I think, maybe not the right question. Maybe you can even cast all problems as function approximation, as some people are advocating that you can cast all problems as optimization problems, right? So whether or not you can formulate a problem in a certain way is the question is, what is the right way to formulate it? What is the right way to solve it? And I think whenever we discover or rediscover a new tool, or by some luck get things into our hands that revive old tools, we need to ask ourselves this question, and that's what I think I would want to claim makes me a skeptic, right? I'm sort of trying to say, let's also think about what are the things, maybe even 5 years from now, that you will not have solved, and shouldn't we already now? I mean, should we all now do deep learning, right? Just because right now that seems to work. I think that's a dangerous strategy. So now this is a sort of a scientific meta question, but I think it's something that we need to ask.
While we're talking about religion, to answer Nick's question about problems that we probably shouldn't do with deep learning, things like computing rocket trajectories. If I use Newton's laws, I have a closed form. There's no reason to learn from examples, right? There are lots of cases like that. But getting back to more of an operational definition of skeptic or not, there's a bet that I had with Vladimir Vapnik in 1995. And part of that bet was Vladimir bet that nobody in his right mind would be using neural networks like Linnet 10 years hence in 2005. And Vladimir lost that bet. He lost it big time now. Now, one could imagine asking the same question. If you're a skeptic, you might say that 10 years hence, nobody in his right mind will be using deep learning. And the other side would say, yes, people will still be using it. And I'd come down on the latter case.
This is again, I mean, this is, you're making it black and white. You're saying either I have to be for neural networks or I have to be completely against it. What I'm saying is neither nor. Okay, then I misunderstood.
I said it wouldn't go away.
So I agree. It has never gone away, right? It was always there, and it goes in waves. And I think it's our job to sort of put some damping factor on the waves that we have. And I think we're about to go on a huge wave, or we are on a huge wave. And the question is, is that the right thing to do?
And I found Nick's point actually is one of the exactly right questions to ask, right? Like, what are these areas where we can't do it, right? And I think everybody here in the room should actually ask themselves when they're working on something, is this something where some deep learning guy could come along, right, and just throw a data set in it and solve my problem in their technique rather than, let's say, the technique that I'm using right now. And to me, it's not clear what these areas really are in the end, right? So, for example, if you think about manipulation, object manipulation, you can approach this very much in a model-based approach, right? Reasoning about friction and all these kind of things. My feeling is that that's actually going to be something where deep learning style techniques, much more, let's say, data-driven techniques, are clearly going to be far superior to the kind of model-based approaches. Even though I'm sure many model-based people would say, no, that's totally wrong, and I'm going to stick to my approach, which is fine, right? But I think at least people should follow a little bit what's going on in the deep learning community and then see, is this something that I can use in my domain, and should be open-minded.
Can I suggest a bet? We're talking about bets. So had Newton not lived yet, and we wouldn't have Newton's laws, maybe we would be predicting rocket trajectories with a neural net now, right? That's I think conceivable. But once Newton is born and is sitting next to the tree and is watching the apple, we would say, that's the answer. We don't need the neural network anymore, right? So here's a claim. It's really a claim. I don't actually believe it, but here's a claim. I think that we can discover new solutions with deep neural networks, but once we understand what's actually going on, we will want to replace them with something that's, to speak with Nick, model-driven, non-hyperparametric.
I've got a few...
Just a very quick one. But are we better at catching apples since Newton came up with the laws? No. So people were able to catch apples without any notion of these laws, right? So just having these laws in there doesn't really mean that we can do certain tasks better.
I was talking about rocket trajectories.
I got a few...
I'm talking about robots like...
I've just got a few comments from the
I have
audience.
a different... I
or
think
not.
can I ask... Sorry, did I interrupt?
Go, Ashutosh, go.
It's a simple thing. Like in 2005, I started my career as a PhD student. I took this convex optimization class, and it didn't go away. I still use it while doing deep learning. Some of the optimization techniques are actually convex. In my last year of PhD, I did learn some other techniques. I still use them. And then I learned kinematics while doing robotics, and we still use them. I think deep learning is going to be one of the techniques. And in fact, what we are seeing already is that deep learning is just not a magic thing that you throw something in, something comes out. Even the recent papers in deep learning have been trying to marry with the other techniques. For example, in natural language, you combine the structure with something else. You have model-based things, you have this, you have incremental learning, you have reinforcement learning and deep learning now going together. So I think the question that we are trying to answer, I agree that deep learning is never going away. But at the same time, someone else said in the talk in the afternoon, there will be something else that will always keep coming up. So we should also watch out for that.
I got Matt in the back there, and then a couple others.
AlphaGo. Next question.
So I would, hello. Matt. I would mention AlphaGo, and
oh yeah.
I think that the problem is not being better than becoming better than human at tasks. I think that almost any individual single task that you define for a human, we would be able to get to a point where a neural network or a robot could do that one task better. The problem is generalization. The problem is being able to do multiple things.
Matt?
Oh, can I add one more thing there too? How we assess performance is very important when we're trying to understand whether or not a system is better than a human. The game context is fairly well defined, but with vision, what do we look at? Is it average accuracy, precision, recall? I suggested earlier that visual psychophysics is probably the better way to look at this. If we don't understand perceptual thresholds, it's really hard to say whether or not the system is actually better or how well it is in general.
And I just want to also remark on AlphaGo. I see this as a great example for that it's not just a big network you throw at your problem, right? It's not just a deep Q network that they trained on playing Go, right? It's a combination of deep learning, smart design of the networks, and the combination with Markov chain, Monte Carlo tree search, and those kind of AI-based search techniques that really are going to succeed on very complex tasks.
Matt?
I think, everybody's been around long enough to see these hype cycles, and one of the things that particularly scares me about deep learning, I don't know if this makes me a skeptic, is that we become so hyped about it, and then additionally the public perception of it, how it's portrayed in the media, and the way that we kind of are seeing it, I can't imagine there's not going to be a backlash if we don't figure out how to solve everything in the world 5 years from now, right? So one of the big concerns is if you're doing neural net research in the 90s, there was a period of time at which you could not get a paper published if you're still putting neural nets in your paper, and we're going to see the same thing here, right? So it's the same thing with SVMs, it's cycles of machine learning. Can we, again, to make it a meta question, how do we prevent in robotics from us getting really, really overheated about a subject and then everybody freaking out when it doesn't fix everything we want to fix?
So I think that's a really good question. I don't know. People get bored with the same things after a while, and so I think maybe that will happen. But I think one thing that's quite different is every 0.1% improvement in your recognition algorithm in whatever machine learning problem you're solving, if it translates to better ads, it translates directly to revenue. So it seems that right now, industrial activity, even if the needle is pushed too slowly for researchers maybe to continue to be excited about yet another 0.1 or 0.2%, it seems like there will continue to be money to support those even very incremental progresses until maybe then there is another breakthrough. So I don't see people completely leave the field, even if most people would get bored somehow. I also would like to actually ask the reverse question slightly, which is, might also be worthwhile thinking about if, let's say we look at supervised learning, and it's maybe fair to say like big enough data set, big enough compute power, supervised learning is pretty much done. Like, just it'll do it. The deep neural net will do it for you. And that took like 5 years, essentially, of leveraging the kind of compute power that seems to be necessary. Like, maybe since 5 years ago, the compute power exists to do this, the data exists to do this, and now it's there. So interesting to think, like, how much compute power is really needed to do the same thing for reinforcement learning, and is it already now? And then is it going to take also 5 years of research for that to be cracked? Because if that's cracked, it gets much more intriguing, because now you have an agent who actually goes around and does things and tries to achieve objectives, whereas a supervised learning system is very contained. But it's kind of the opposite of the bust scenario.
I'm going to have to stop there. There was a couple more questions, but we've run out of time. I apologise. Most people will be around for the next couple of days, so please go and talk to them and ask them more hairy questions. Before we wrap up, I just wanted to thank a few people. First off, I want to thank the panel for speaking today, as well as dealing with the hecklers. Really appreciate it. Thank you. Thank you to all the contributed papers, the speakers for today, and putting the posters together and the papers. They're all fantastic. It was really inspiring, for me at least, to see all these submitted at a workshop at RSS. So thank you. I wanted to thank the sponsors, ACRV, the Australian Centre for Robotic Vision, and Skydio. Frank, thank you for coming, Frank. Really appreciate it. So thank you, guys. I want to thank the two people that I think really put most of this together, Nico Sunderhoff and Yuxi Leitner. Really great workshop. And thank you everyone for coming and heckling. Have a great rest of your conference.